Alright, so today, Chapter 10, Section 1, the definition of an nth root. Alright, we're good to go. Alright, so the definition of a square root. The reverse operation to squaring a number is to find its square root. For example, finding a square root of 36 is equivalent to asking when squared, what number equals 36? One obvious answer to this question is 6 because 6 squared is 36. But we also know that negative 6 squared will also be 36, right? So the definition of a square root is nothing new to you. B is a square root of A if B squared is equal to A, right? Because if we took this is equal to A and then took the square root of both sides, right? We are muted. Thank you. Can you hear me now? Alright, so the all I did here was I just basically read the that statement, and I'm going to be showing how B is a square root of A if B squared is equal to A, because we've got B squared is equal to A, and if we take the square root of both sides, right, so we end up with B is equal to plus or minus A. I'm sorry. What did I do wrong here? No, I should keep it like that. Sorry. Yeah, just keep it like that. Really no need to discuss that any further. I am all over the place again. Alright, so let's just do something easy and identify square roots, right? This is getting a lot of control. So, identifying the square roots, we've got for 25, what is the square root of 25? So, the thing is, for your squares, typically you want to memorize them up to 10 at least, right? 10, maybe up to 15 if you can, but mainly 10, the first 10, right? And then cubes mainly like the first 5. And we went over that before, and plus there's a chart later on whenever we do get to it. It'll be nice and clean for you. But square root of 25, well, that's just 5. The square root of 49. I'm sorry, the square root of 49. Well, that would be 7. The square root of 0 is 0. And then lastly, the square root of negative 9. Okay? So, negative 9. We know that the square root of negative 9 is a number, right? But at this point in time, in this text anyways, we haven't gotten to imaginary numbers yet, okay? So what we're going to say is that there is no real number. No real number. Okay? And of course, the question even asks, identify a square root as a real number. Okay? Now again, we do know that negative 9 does indeed have a square root on the imaginary plane, but for today's lecture, we do not have a solution to the square root of negative 9. Okay, let's actually look at the tip. Let's bring that tip into, and yeah, we'll do that. Okay, so here is a really good tip. All positive real numbers have two real valued solutions, one positive and one negative. And we see that whenever we take the square root of both sides of an equation, we would say, for example, it would have been in my first one, but I guess we can just go back to that. Okay, if we took the square root of both sides, okay, then we would indeed have b, the square root of b squared is b, is equal to the plus or minus square root of a. Okay, so we do indeed have two real valued, one positive and one negative. Okay. 0 has only one square root, which is 0 itself. That makes sense, right? I mean, we could follow the same practice and say, plus or minus 0, right? But we know 0, the square root of 0, or yeah, the square root of 0 is just 0. And then a negative number has no real valued square roots. Okay, whenever we say real, we're talking about a specific kind of number, real numbers. Okay, we're not talking about, you've heard integers, um, uh, natural numbers, things like that. Real numbers encompass every one of those numbers. Real numbers encompass every single possible number except for imaginary numbers. Right. And down here, we've got, recall that the positive square root of a real number can be denoted with a radical sign. So we don't do it here, so never mind. So let a represent a positive number, then a, or 1, the square root of a is the positive square root of a. The positive square root is also called the principal square root. Okay? And then 2, negative square root of a is the negative square root of a. And then 3 would just be the square root of 0, right? Square root of 0 being 0. Excuse me. Okay, so getting these square roots, this asks us to figure out what square roots are, right? Simplify the square root. So what is the square root of 36? So it's basically the same exercise as example 1, except now we have the radical, okay? Now, be careful not to put, for questions like this on your homework or your test, don't put plus or minus 6. Okay, some of you might be like, well, no, duh. Well, I do get some people, and it's fine. You do get into into an autopilot mode sometimes, right? You usually incorporate something new that you just learned, and we know that this is not the case for this one. So the square root of 36 is just plain old 6, right? And b b is going to be a good one. So if you've forgotten how to, I don't know if I don't think it was actually in the reviews. So if we have the square root of 4/9, so I'm going to go ahead and rewrite all that being, this, right? All right, if we have the square root of 4/9, all right, recall that the square root of 4/9 is the same thing as saying the square root of 4 over the square root of 9. Okay, and then that makes it a lot easier to look at, doesn't it? So what is the square root of 4? Well, that's 2, and the square root of 9, that's 3. So the square root of 4/9 is just 2/3. Okay, C. All right, so C, I've asked you to memorize your squares up to 10, right? Well, these are decimals, right? So obviously you don't memorize them, but they do behave, it's kind of the same way. If I would have said the square root of 4, you would say, well, that is 2. Okay. Well, the solution is kind of in the same line, but not necessarily, I guess, because the square root of 0.04. Okay, so we have to ask ourselves, what multiplied by itself would get me to 0.04, and that would be 0.2. Okay. Alrighty, so a non-negative number cannot have a real number as a square root. We've talked about that before. A negative number can have a square root, can have a real number as a square root because no real number when squared is negative. For example, the square root of negative 25 is not a real number because there is no real number b that you can square to get to negative 25, right? I mean, a positive 5 times positive 5 is 25, right? And then a negative 5 times negative 5 is positive 25 as well. So there's no number that you can just square to get to a negative number. So, again, I feel like I'm beating a dead horse. You guys are familiar with the fact that we cannot square negative numbers. So A Start up here. Okay. All right, so A is saying simplify square root if possible. A, what is the square root of negative 144? All right, so we have the negative inside the radical, and this tells us right away that there's going to be no real number, right? So I'm just going to put no real number. Okay. All right, B. Now B is a little bit different. Okay, don't be thrown off by a negative inside the radical and a negative outside the radical. Okay, because we can rewrite B kind of like this. We can rewrite it like this. We can say negative 1 times the square root of 144. Okay. And what is the square root of 144? Well, that would be 12. So it's going to be negative 1 times 12, or in other words, negative 12. Okay. C. All right, well, these are easy problems, aren't they, right? We have another negative number in there, so we're just going to say no real number. Okay. And then D, same thing. We're going to do the negative 1 out front, right? And then it is the square root of 1/9. So remember that I can rewrite that as the square root of 1 over the square root of 9, which is negative 1 times, all right, the square root of 1 is just 1, and the square root of 9 is 3. So we would say this is negative 1/3. Okay. We got a lot of definitions there, all right. Okay, so let's start over here. So the definition of an nth root: finding a square root of a number is the reverse process of squaring a number. We know that. The concept can be extended to finding a third root, called a cube root or a fourth root, and in general an nth root. Okay, n obviously just being a variable, right? An nth root. B is an nth root of a if b raised to the nth power is equal to a. For example, when we see a square, example 2 is square root of 4 because 2 squared is 4, and example 2 is a third root of 8 because 2 cubed is 8, and 2 is a fourth root of 16 because 2 to the fourth is equal to 16. Okay, and before we move on to the next definition, this down here is very handy dandy for you to be able to identify your perfect cubes, fourths, and fifth powers as well. So the radical sign, all right, so this is, okay, good. We're going to say square root, no, let's do it. Okay, so all this up here, is just, I'm going to write it down here. Just basically the anatomy of a radical, and that way whenever I say words like radicals, radicands, index, you'll know what I'm talking about. Okay, so obviously this symbol here, all right, that is just simply the radical, right? Okay, the number or variable or whatever is inside the radical, we call that the radicand. And then this number that we put inside the little divot, right? We call that the index. Or the root. Maybe does that say it over there? No, but it is often referred to as a root as well. Okay, and of course, if there is nothing there, if this is empty. We know that it is an implied square root, right? All right, so that takes care of that. Okay, so next we're going to be talking about evaluating the nth root of a. If n is an even integer and a is greater than 0, then the nth root of a is the principal, again positive, nth root of a. For example, we have the fourth root of 625, which is 5. If n is greater than 1 is an odd, if n greater than 1 is an odd integer. Okay, so basically it's saying if, well, the first example, this first one, would be if we have an even index, square root, fourth root, sixth root, so on and so forth. The second example would be if the index here is a first root, well, first root, cube root, seventh root, sorry. Then in the nth root of a is just the nth root of a, right? And then if n is greater than 1 as an integer, then the nth root of 0 is always going to be 0. Okay. So again, we need to be able to recall these cubes, perfect cubes, perfect fourth powers, perfect fifth powers. Admittedly, I guess I do. I think it's just something you just kind of develop over time, the fourth and fifths. Actually, let's put that with this. Okay, so A, we have the, simplify the expression if possible. Okay, so A, the square root of 4, that's just easier, that's 2. All right, B, the cube root of 64. Okay, so this is where you have to, memorization does come into play here, but for today's sake, you know, we can kind of look at this chart here, looking for cubes. Okay, so what is the cube root of 64? Okay, well, what times what times what will give me a positive 64? And if I look at this chart, it looks like just a 4. Now, C is a little tricky because, C is a little tricky because you might be tempted to say, okay, well, we've got a negative as the radicand. Again, the radicand is the number inside there. Okay, so we've got a negative number as the radicand here. All right, so it must be no real number, right? Right, no real number. Right, but check this out. All right, so it's let me make it a little bit larger here. It is the fifth root of negative 32. Okay, so if I were to go that line of thinking and just say, you know, every negative number I see here is no real number, I would be wrong, right? Because the fifth root of negative 32 is basically saying, you know, what times what times what times what times what is equal to negative 32. Okay, well, looking at the fifth powers here, we have a 32, so 2 to the fifth is equal to 32. So I'm going to say that negative 2 times negative 2 times negative 2 times negative 2 times negative 2 is equal to 32. Okay, so let's do that. So negative 2 times 32, I'm sorry, negative 2 times negative 2, that's positive 4. This right here is also positive 4, and then we have a negative 2. Okay, well, 4 times 4, that's 16, and then 16 times negative 2 is a negative 32. Okay, so we do see that when we can have negative radicands in an odd index. Okay, so let's break that down again. We can have negative radicands, this number here, in an odd index. Okay, we just cannot have negative radicands in an even index. Right, the square root of a negative number, the fourth root of a negative number, and so on and so forth. So C would be negative 2. Right, D. All right, so the fourth root of 81. Okay, so we would again look up right. We'd look up here. Fourth root. What fourth root gives me 81? Looks like 3. So that's just 3. Okay. Oh, the 6th root of 1,000,000. Okay, so how do I get the 6th root of 1,000,000? Obviously, you know, you'd be like, oh, I'll just use a calculator, and I mean, I guess you can, but we would basically be asking, you know, what magnitude of 10, right? If you multiplied it, you know, 6 times, well, I give away the answer. Yeah, I'm going to say 10. But it is what times what times what times what times what? Did I miss one? What times what times what is equal to 1,000,000, and that would be 10. Okay, and then G. All right, G's again. We're going back to the simple one, right? We have it is the 4th root of -16. Okay, so this is an even index, and we have a negative radicand. Okay, if this were odd, I skipped F. I did skip F. That was on purpose. No, yeah, I did skip F. I'll go back. If it was an odd, then there would be a solution there, right? But since we have an even index, then we can comfortably say that G is no real number. Okay, and we'll do F last. But I mean, I guess F and G are kind of the same, right? Because it is an even index, right? There, you don't see an index, so that's an implied 2, so it's a square root. It's a square root of a negative number, right? Square root of -100, so same thing. No real number. Okay. All right, so roots of variable expressions. Finding an nth root of a variable expression is similar to finding an nth root of a numerical expression. For roots with an even index, however, particular care must be taken to obtain a non-negative result. Okay, so if we are looking at evaluating the nth root of a to the n, okay, so if we evaluated the nth root of a to the n, if n is a positive odd integer, okay, so basically, you know, just some odd number, right? We say odd integer because, you know, what is an integer? An integer is a whole number, okay? So if n is some positive odd whole number, then the nth root of a to the n is just simply a to the n, okay? However, for like number 2, if n is a positive even integer, then the nth root of a to the n is equal to the absolute value of a. So the only difference between these two would simply be, is the index even or odd? Okay, if it is odd, just deal with it like you normally would. If it is even, then we will incorporate an absolute value symbol. Okay, doesn't mean it's going to stick though, and we'll see what I mean by that here in a moment. So a is the 4th root of -3 to the 4th power. Okay, so again, we are evaluating equations where we have the radicand raised to some power, and that same power is also the index. Okay, and we see that like in A, we have the -3 raised to the 4th power, and we have a 4th root. Okay. So what is the 4th root of -3 to the 4th power? Well, you would say that we have an even index, so we would say it's going to be the absolute value of -3. Okay, but we also know that the absolute value of -3 is simply 3. B, we look at our power and our index, and they're both odd, right? It doesn't matter what, I mean, it could be, you know, 77. It doesn't matter what the index is, right? As long as the index is the same as the power attached to a number inside the radical, we're okay. So it's a 5 and a 5. They're both odd. So this tells me that all I have to do is just take that value, right? It's just simply the value. And that value is just going to be -3. Okay, C is where the absolute value stuff kind of gets a little more tricky. Okay, so in A, we had the absolute value of -3. We know the absolute value of -3 is 3, right? Well, for C, okay, notice we have an even index, and the radicand inside is raised to a second degree, second power, right? So we would say the absolute value of x plus 2 because, you know, again, the index and stuff is, they're even. Well, we're going to leave it at the absolute value of x plus 2 because we don't know the value of x, okay? So unlike A, where we know for a fact the absolute value of -3 is 3. For C, we can't really go on beyond this because we don't have the information needed. Okay, so we have to leave it as the absolute value of x plus 2. Okay. D, right? That's a 6 and a 3. That's 6. Interesting. I don't think that's supposed to be a 6. Yeah, it's not. Yeah, it's supposed to be, yeah. I was wondering why we jumped ahead. So yeah, even our solution down here has this has a cube root of cube. So that would be the second typo we've spotted. Well, I won't say this week. I guess in the last 2 lectures. But anyways, it should be the cube root of a plus b cubed, all right? And so that would just simply be a plus b because, again, they're both odd. 6th root, man, that would have thrown me all off. Okay. Now E is not a typo, okay, because we can think of this as the square root of y squared, right? Everybody agree that y squared is the same thing as y to the 4th power? All right, we're done. All right, so this would be the absolute value of y squared, okay? But excuse me. But similar to A, we know that anything squared is going to be a positive number. You cannot square a number and get a non-positive number, right? So same as A, sort of. We can just kind of write this as simply y squared. All right, maybe we'll add that. Okay, so if n is an even integer, then the nth root of a to the nth power is the absolute value of a, right? However, if the variable a is assumed to be non-negative, all right, non-negative is basically, you know, it's encompassing the natural numbers, right? So non-negative numbers are obviously numbers that are not negative, but also include 0. So whenever we say non-negative, that's what I mean by that. Then the absolute value bars may be dropped. That is, the nth root of a to the nth power is equal to a, provided that a is greater than or equal to 0. In many examples and exercises, we will make the assumptions that the variables within the radical expression are positive real numbers. In such a case, the absolute value bars are not needed to evaluate the nth root of a to the n. Okay, and we saw that for 2 of our examples on in the previous example, 2 of our problems on the previous example. So take a minute to examine the following patterns associated with perfect squares and perfect cubes. In general, any expression raised to an even power is a perfect square. An expression raised to a power that is a multiple of 3 is a perfect cube. Of course, that makes sense, right? Perfect squares, perfect cubes, you know. These patterns may be extended to higher powers. Okay, so we're going to wonder if I can just put this on the same page. It's only 4 problems, right? I'm sure we can do that. Squeeze it down. Okay, let's try it. All right, so A. Alright, so a is the square root of y to the 8th power. Okay, so we have y to the 8th power. Well, how can I rethink y to the 8th power and simplify this problem? Right? Well, there's a couple ways we can go about doing it. I'm going to do it both ways that I like. Okay, so the first one, and the way the book is probably wanting us to go, is to reduce the square root of y to the 8th power down into something that is a perfect square. Okay, so that would be y to the 4th squared. Okay, y to the 4th squared is indeed y to the 8th power. So all I do is just rewrite this, and then using our technique that we used on the previous example, then we know that this is just going to be y to the 4th power. Right? Now, and I might be jumping the gun here because I'm pretty sure we will be talking about this later, probably in this chapter. But there is a way to rewrite radicals. I'm not going to get into that just yet. I don't want to be confusing. But notice how, at least, well, all right, I'm this far. I'll say it anyways. All right, for variables, okay, not necessarily for the numbers that we're about to see here, but for variables, okay. Y to the 8th power, well, that is an 8th, it's raised to the 8th power, and we have the implied 2 here. You have the implied 2 right there, right? Well, then you can just simply say 8 divided by 2. 8 divided by 2 is 4, and then that's how we get y to the 4th power. And I think I might have done you a disservice throwing that in there before we get to it, but let's incorporate that for b, okay? So this is the cube root of 27a cubed, okay? Now I said this only works for the variables because I'm not going to be dividing 27 divided by 3, right? That's 9. That doesn't make sense. All right, the reason why I divided the variable is because if you recall, when you no. All right, so the cube root of 27 is 3, right? 3 times 3 times 3 is indeed 27, all right? And then a cubed, what is the cube root of a cubed? Well, that's just a. Okay. And then c, okay, d, I think d will be more in line with the example of a, okay, because it's not the exact same. So anyways, c, we have the 5th root of a to the 5th over b to the 5th, okay? Well, all the index and the powers, they're all the same. So it's just going to simply be a over b. Okay? And then d, let's put out here. All right, so we have to go back and think about what we had earlier with the 4th roots, right? So this is going to be the -1. So we're going to put -1. Okay. -1. All right, so what is the 4th root of 81? So what times what times what times what is equal to 81? And if you recall, it would be 3, right? 3 to the 4th is 81. If somebody just joined, can you please mute your mic? So anyways, so we would say, well, that's going to be a 3. And it's in the numerator, so I'm going to put it up here. So 3. And then what is the 4th root of x to the 4th? Well, that's just x. And then what is the 4th root of y to the 8th? And this is where, again, I just did the quick division, right? It would say 8 divided by 4 is 2, so we would say y squared. And then that is divided by 16. So what is the 4th root of 16? Well, that's just 2. Okay. Well, it's -1 times 3xy squared divided by 2, or we can just simply say the negative of it. Okay. So yeah, so I might have jumped the gun a little bit, just trying to help you out. We'll see. Okay, so there are a few things that even your parents remember about mathematics, and one of them is the Pythagorean theorem. Okay, so given a right triangle with legs of length A and B and hypotenuse of length C, the Pythagorean theorem can be stated as a squared plus b squared is equal to c squared. Okay, so the Pythagorean theorem is a lot more important and is a lot more used than you have any idea of. Okay, because whenever you can, especially in calculus, whenever we get to like word problems in calculus, a lot of the times you can break something down into a triangle, and if you can break something down to a triangle, then you can use the Pythagorean theorem. Okay, so hopefully at this point you've also have it mindlessly memorized because it's super easy, right? A squared plus b squared is equal to c squared, where c squared is the hypotenuse. Oh, maybe I should snip the triangle, huh? Okay, so this wants us to find that missing leg. Okay, so again, whenever we break down the Pythagorean theorem, a squared plus b squared. Okay, so these two are just the two shorter legs of the triangle. Okay, or not hypotenuse, right? And the c squared is the hypotenuse here. Okay, so it doesn't matter what you put as a and what you put as b. It's just that c always has to be the same. So what I mean by that is in this triangle, we have this leg. Well, yeah, we have that leg as our just one of our legs. This is our other leg, but 13 is a hypotenuse. So 13 must be the part that gets that's all by its lonesome over here. It'll be 13 squared. Okay, so let's write this out. So we're going to denote this question mark. We're going to call it A. Okay, so we're going to say A squared plus 5 squared is equal to 13 squared. Okay, but again, I said that the legs don't really matter, so it could just as well, we could call this leg B. Okay, we could just call it B. So it could be 5 squared plus B squared is equal to 13 squared. Okay, again, as long as you have the hypotenuse correct, you're going to be in business. Okay, so let's solve these one at a time. All right, so a squared plus, all right, 5 squared is 25, and 13 squared is 169. And maybe I should just, all right, maybe I'll just do one of them because I don't want to skip some of that computation. Okay, so we'll just go ahead and write it out as if it was squared. Okay. All right, now I have to solve for a, right? So by solving for a, I need to subtract 25 from both sides. So I'll have a squared is equal to, well, 169 minus 25 is a nice perfect square, 144. And then if we take the square root of 144, okay, we would say a is equal to plus or minus 12. Okay, now here's the thing, and this is going to work for every one of our triangles. So when we talk about distance, again, we don't talk about negative distances, right? Because somebody says, hey, Sherman, how far away is Kroger? I don't say, oh, it's negative 3 miles this way, do I? No. So I wouldn't say the negative, and of course I just don't even have to say positive either, do I? So A is just simply 12, okay? So the third side of this triangle is 12 units long, okay? Yeah, 12 units long. Well, I guess it would be feet, right, because it's using feet. And that's it. That's how we use the Pythagorean theorem, okay? Everything, these two legs, they can be interchangeable. The only thing that has got to be set in stone is you must do the hypotenuse correct. The hypotenuse is always going to be the number all by itself on the other side. Okay. Oh my, what is this? Is this a word problem? You know, I feel like for many of you, I was I don't know. You guys actually seem like a really good bunch, actually. So maybe I'll say my other classes. When I was taking these courses in my first couple years of college, I wasn't going into mathematics, so I was just like, I hate this. This is dumb. Why do we have to use this? And of course, I know all these reasons and why now. But one of the things that I did, and again, I was a horrible student at first. It was whenever I would get to a word problem or a problem that we didn't do much of, I would just think, well, I hope there's not a lot of these on the test, and just move on, right? It was a horrible attitude to have. But I would look at a problem like this and I'd be like, yep, not doing it. I'd go to the next one, right? But if I would have, and for you as well, if you just slow down and be like, and you actually read it, well, it's not that hard and it doesn't take that long at all. Okay, so let's go ahead and read this. So 2 boats leave a dock at 12 noon. One travels due north at 6 miles per hour, and the other travels due east at 8 miles per hour. How far apart are the 2 boats after 2 hours? Okay, so the thing is, it does this isn't even this is not really even a time hour kind of thing, really, right? I mean, I guess it kind of is, but the whole point of this is to use our Pythagorean theorem. Okay, so let's see. I might have. Let's see. Yeah, I might have not. I might. Well, it was part of the problem. Okay, so I was thinking I should not have snipped that first because these numbers aren't 100% in line with our Pythagorean theorem or with the information given. Okay, so let's break down the information given. So if 2 boats leave a dock at 12 noon, one travels due north at 6 miles per hour, and the other travels due east at 8 miles per hour. How far apart are the boats for 2 hours? So that's really all the math that you kind of quick math you have to kind of do, right? Is that they've traveled for 2 hours. And one's traveling 6 miles per hour. Well, 6 times 2 is 12, and that's where we get here. And then 8 times 2 is 16, and that's where we get that. Okay, so I might have jumped the gun on snipping the actual triangle, but again, it doesn't say solution yet, does it? No, the solution's underneath it. Okay, so anyways, from here, all we have to do is just do the Pythagorean theorem, right? So Pythagorean theorem is a squared plus b squared is equal to c squared. Okay, I feel like you already have that memorized. So this would be 12 squared plus 16 squared is equal to c squared. Now again, it doesn't matter which leg is which. Okay, I could have just as well interchanged these to be, 16 squared plus 12 squared. But addition is commutative, so again, it does not matter which side was which. And my air conditioner is on and I'm freezing. And so 12 squared is 144 plus 16 squared, which is 256. That's equal to c squared. Okay, so 144 plus 256, that is 400. That's equal to c squared. And then we take the square root of both sides, and so we have c is equal to 20. Okay, so these 2 boats after 2 hours are 20 miles apart. And again, it's not that difficult. You just have to break things down, look at them. Don't be a lazy student like I was. Actually take the time to do it. Okay. So yeah, I was pretty horrible, but look at me now. Okay, so if n is an integer greater than 1, then a function written in the form f of x equal to the nth root of x is called a radical function. Okay, so everything today, we've had equations and stuff, right? But now we're going to be talking about functions. Okay. Note that if n is an even integer, then the function will be a real number only if the radicand is non-negative. So if n being our root, okay, so n, if it is an even number, then it will be a function with a real number only if the radicand the number inside my radical is non-negative. Again, 0 or above, right? Therefore, the domain is restricted to non-negative real numbers, or equivalently, from 0 to infinity. If n is an odd integer, then the domain is all real numbers. Okay, so let's look at A. So this is wanting us to find the domain and put it in interval notation. So A, all right, the fourth root of t minus 2. Now, if I've bored you this far, you have to pay attention here. This is big time stuff here. Very important. If I want to find the domain of a radical expression, okay, a radical function, and my index is even, all right, what I must do here, okay, is I have to take the radicand, all right, and that's t minus 2. Okay, I know my radicand must be non-negative, right? And so how would I write that? Well, I would say, non-negative would be any number that is greater than or equal to 0. Does that make sense? So I need to make sure this number here, okay, again, which is the same number inside here, I'm going to figure out what numbers that I can use, okay? And by setting it setting it to greater than or equal to 0, I will then find out what numbers that I can use. Okay, so I would solve here, and I would get t is greater than or equal to positive 2. Okay, so what does that mean? Well, I can use any number imaginable that is greater than or equal to 2. And of course, we can work that out, right? Well, let's just use the number 2. Well, 2 minus 2 is 0. The square root of 0 is 0. That's good. 3 minus 2, that's 1. Square root of 1 is 1. Okay, so, I can use any number that is greater than 2 in order to work. Well, let's choose a number that's less than 2. All right, like 0. All right, or we'll start with 0. Well, 0 minus 2, well, that's negative 2, and the fourth root of negative 2 is not a real number. Okay, if we use, 1 is less than 2, 1 minus 2 is negative 1, and we know that the fourth root of negative 1 is also not a real number. So that's how we find the domain of a of a radical function, right? And of course, it wants us to write an interval notation. So how do I write t is greater than 2 in interval notation? Well, I would say from 2 to infinity. Okay, those are all the numbers that I'm allowed to use. All the values that are greater than 2, which it would be in interval notation, 2 to infinity. Okay. B, luckily B is nice and easy for us, isn't it? Okay, excuse me. Because we have an odd index. Okay, since this is an odd index, this up here reads, if n is an odd integer, the domain is all real numbers. So that's easy. So we say, well, this number is 3 is odd, so the domain is going to be all real numbers. If I write that in interval notation, it would be negative infinity to positive infinity. And then C we're going to have to do similar to A. Okay, so it is an even index, so I'm going to have to set the radicand to greater than or equal to 0. So we would say 3 minus 5x is greater than or equal to 0. Okay, and then if I solve for x, okay, we would say negative 5x is greater than or equal to negative 3. Or, and then if I divided both sides by a negative 5, recall that you have to switch this, or flip the sign rather. So it would be x is less than or equal to 3/5. Okay? And that's again me dividing both sides here by negative 5. Negative 5, negative 5. Okay. So the domain of C would be all real numbers that are less than or equal to 3/5. Okay, so I would write that as we would go from negative infinity on the number line all the way to a positive 3/5 and stop. Okay, that's how we find the domain of radical functions. Now it does get a lot harder and a lot more tedious whenever we have a second degree polynomial as a radicand. And I don't know if you recall, but last week we were well, I forgot what we were doing, but what we did was we had a number line and we put up walls and we had intervals, if you recall, okay, and we did test points. That's why we did that exercise, because whenever we talk about numbers inside of a radical, if it is a secondary polynomial or greater, we have to do that long tedious process that we did practice last week. And I think this might be the record for the longest we've had a lecture, isn't it? Okay, so graphing. Okay, we'll do the domain, and then I'll leave the graphing up to what the book actually shows instead of me trying to make it nice and pretty. So this wants us to write the domain of f in interval notation. So first things first, we're just going to have to find the domain, right? So the domain, I'm going to set my radicand, 3 minus x. I'm going to set it to greater than or equal to 0. Okay, and then in order to solve this, you recall we have to we just have to solve for x, right? So if we divided both sides by our subtractives, we would have x is less than or equal to a positive 3. Okay, and then if I wrote that domain in interval notation, that would be from negative infinity to a positive 3, and that's it. Okay, and so like I said, I'm just going to go ahead and do the graphing. Let the textbook do the graphing. Okay, so notice how we could only use values that are less than 3, right? Looking at the domain here, it's from negative infinity to positive 3. So we're going to look at all the values that are, 3 and less. And that's what we're doing here. We're creating a table. Create a table of ordered pairs where x values are taken to be less than or equal to 3. We do that, and then we can make this table. We have an x. These are my x coordinates, and these are my y coordinates. And then we can plot those points, and we see that we have this equation, this square root equation function going backwards. Okay. And I believe that does conclude the lecture. Yeah, that does conclude today's lecture.